Terrific. Welcome, YouTube. Our speaker today is Craig Kaplan, who is a computer scientist, mathematician, and mathematical artist, and a professor at the University of Waterloo, and just this week was made a distinguished member of the ACM. He's very involved with the mathematical illustration community, both as an editor of the Journal of Mathematics and the Arts and as an organizer of the Bridges Conference on Mathematics and Art. Kaplan's work primarily focuses on applications of geometry and computer science to visual art and design, and he was part of the team that delivered us the aperiodic monotile, a single shape which aperiodically tiles the plane but cannot do so periodically. So we're super excited to have Craig join us today. The floor is yours.
Thank you very much. It's really thank you, Brian. Yes, I'll be here all week. It is a pleasure to be here. If I remember correctly, the genesis of this was that when Aaron told me about the IHP program, I said, I'm trying very hard to avoid air travel, so I don't think I'll go to Paris. And as a consolation prize, we agreed that I could give one of these talks. This is great. This is my honorary contribution to the IHP program, I guess.
We're very happy to have you.
Well, I'm happy to contribute. I mean, this has been a great series, and it's been fun to watch every time I'm able to. Let me get in there. Okay, so I should be sharing now. So I want to talk about some old work. This is something that I've been thinking about. Well, I mean, at least 25 years, because I mention it in passing in my PhD thesis. And some people may have read a blog post I made about this back in 2019, but it occurred to me in the ramp up to this talk that I've never given a talk about it or published a paper for that matter. So it seemed like a decent opportunity to go over it. It's not mathematically all that sophisticated. The ideas are pretty elementary, I think, just some basic algebra in the complex plane. But in a sense, I think that's its virtue. This is not research about doing something really complicated. Rather, it's something I enjoy, which is research that shows that something that looks complicated actually is quite simple if you look at it the right way. And it's always nice to keep those ideas in mind so that that's a tool that you might be able to use at some point in the future when you realize, wait a minute, like I don't need to make this more complicated than it is. But it is more math art. It's also, I was motivated by, you mentioned the hat. My life has been an endless sequence of talks about aperiodic monotiles, which has been great because everybody wants to hear about it. As recently as a week ago, last Friday. And so I resolved to give a talk here that was hat-free. So you will not be seeing aperiodic monotiles in this talk. That's by design. All right, so I will talk a little bit about Escher. There are some nice math art connections here. I mean, Escher's right there in the title. So let me say why these particular spiral tilings are Escher-like. Some of you may know M.C. Escher, the artist, was one of his obsessions was with infinity, with how do you depict an infinite world, the totality of an infinite world in a finite canvas. And he explored this theme in a bunch of different ways. One common way that he explored this was to try to depict an infinite tiling. And one way that he did that was to have tiles that diminished in size concentrically toward the center of the design, where you arrive at what you sometimes in tiling theory you can call a limit point, which is a term that you would be familiar with from calculus or topology. It would be a point where every neighborhood of that point contains an infinite number of tiles. And so you certainly are depicting an infinite number of tiles, at least conceptually, in this drawing, in this woodcut. And that was from 1956. So let me show you a bunch of, here's sort of the subset of Escher's work that deals with this particular idea of having a limit point at the center of the drawing. He had three that were called Path of Life, with these kind of abstract fish-like creatures and different orders of symmetry. I guess it's 8 on the left, 4 in the middle, and 6 on the right. An older print, Development 2, This one is particularly dear to me because it combines the limit point with something like a parquet deformation, which is something I won't talk about today, but something I'm really interested in, where you can see that the tiles evolve from being pure hexagons in the center to the lizards of one of his famous symmetry drawings on the outside. And that's really it's a very effective drawing because like you lose resolution at the center of the design of the composition. And so it actually kind of makes sense that you would evolve the tiles to be simpler and simpler towards the middle. It creates a really nice composition. And then a much more elaborate one is, circle limit with butterflies on the right there, which again, this one is maybe a little bit related to sky and water in that the tiles are a little more abstract and geometric in the middle, but evolve and kind of fly free from one another towards the outside. Now, as we know, towards the end of the 1950s, Escher found a completely different solution to this problem, the solution of using hyperbolic geometry and creating tilings in the Poincaré disk. I think this overlaps a little bit with Vladimir's talk from last month, and there'll be a couple of other places where we overlap. No problem there. Here, I mean, this is a very different solution, and it would be much harder for a non-mathematician to find working independently. And of course, the story is that Escher found this after studying a diagram in a book by Coxeter and basically reverse engineered the construction of regular tilings in the Poincaré disk from the drawing without understanding any of the math directly, which is just mind-blowing. But here we have a different thing where he really is able to depict the entirety of an infinite tiling of a plane in a finite canvas. Whereas anytime you have this limit point in the middle, you have to make an arbitrary decision of where to stop drawing tiles. And that was never fully satisfying to Escher. And then the one maybe most remarkable example of this style is snakes on the right. This was the very last print that Escher made, 1969, and it does both, right? Effectively, the geometry is a hyperbolic tiling in the Poincaré disk on the outside of the disk, and then that is linked together with one of these limit point tilings that diminish towards the center of the disk, and the whole thing kind of comes together smoothly. It's really just a monumental achievement. Now, we're not going to spend any more time talking about hyperbolic tilings today, but it was really necessary. If I'm going to talk about this stuff, it's important to say what the answer was from Escher's point of view. The circle limits here were like kind of the ultimate way to depict infinity in some ways. Okay, now the point I want to make about these tilings, the spiral tilings with central limits, is that it turns out that it's very easy to draw them if you use this one weird old trick. That's the central point of this talk, is that you don't actually have to work that hard to turn a periodic Euclidean pattern into one of these limit spiral tilings. And that's what I'll basically explore in the rest of this talk. The technique, as I said, is elementary. It really only relies on some very basic functions in the complex plane, but it ties together with some of the work that I've been doing since my PhD on symmetry and tiling. So if you know that what you're working with is a tiling of the plane, you can tie that into the complex math in a nice way to get cool pictures and explore the degrees of freedom that are available. I certainly don't claim to have invented this myself. I'm not quite sure how far back it goes or even where I learned the ideas in the first place. It is back when I was doing my PhD, I was at the University of Washington, and I was lucky enough to occasionally have direct contact with Branko Grunbaum, who is like the god of tiling theory. And I think it's very possible that he showed this to me directly in his office. Like, well, why don't you just do this? And it would have been very obvious to him when he was talking about this. All right, so the core idea, the one tool you really need is the exponential function in the complex plane. So let me just break this down for you. So if you have a complex number z, we pass it through e to the z. What does that mean in practice? Well, if my complex number z takes the form a plus ib, a plus bi, then I take the exponential of that. And of course, I can break that apart using, laws for exponents to turn that into e to the a, e to the ib. And then I use Euler's formula on e to the ib, and I discover that the point a plus bi through the exponential function gets mapped to a point in the complex plane that is of distance e to the a from the origin and at angle determined by b, cos b plus I sine b, around the origin, right? So its distance is e to the a, and like the azimuth is b. All very elementary math. There shouldn't be any surprises there. This was, I think I discovered this in a paper by Dixon in 1992 called Two Conformal Mappings, where he referred to this as the anti-Mercator map because, well, he referred to the logarithm function as the Mercator mapping. So this was the anti-Mercator mapping. It's a really lovely paper. I encourage you to look it up. Where I first saw the Dixon paper, I can't remember. No idea. That kind of bothers me. I thought maybe I saw it referenced in like a different paper about Escher's work, but I looked it up and the reference wasn't there. So it's possible like it's for dumb reasons. Like I was reading a bunch of papers about Escher and this was like next to a paper that I was reading. So, and I looked at it. That's as far as I can remember. So under this mapping, you can start to ask interesting questions. These are nice like undergrad math questions. Like under the exponential map, the anti-Mercator map, what happens to a vertical line? What happens to a horizontal line? What happens to a line in general? Now, to answer questions like that, as I've told my grad students, who are some of whom are here in the talk, hello, I like to answer such questions, but I think in code, right? So what I will do in such cases is write a little program to let me explore these questions. So this is a little interactive tool that lets you draw in the Euclidean plane and shows you the result of passing that drawing through the anti-Mercator map. So if I draw some stuff here, I get like some stuff on the right relative to a center that's presumably somewhere around there. And so now we can ask this question, what happens to a vertical line? Well, let me draw a vertical line. Well, looks like it goes to a circle. Very nice. And if I move that circle around, well, you know, it stays a circle. Nothing else happens to it. So tentatively, vertical lines go to circles. I'll draw a horizontal line. What happens to a horizontal line? Well, it turns into what looks like this weird cone shape, this wedge, but in fact, this is just a line extending radially out from the origin of the complex plane, but it's the thickness of the line that is becoming like wedge-shaped when you project it. And finally, what happens to a diagonal line, maybe most interestingly of all, it becomes this pretty nice spiral shape. I can draw one there. I'll draw another one there. If I'm drawing something that is extending well outside the visible part of that little Euclidean box in the upper left, but you can see that, yeah, as I do that, I get a more and more spirally spiral. In fact, this is a logarithmic spiral, right? An equiangular spiral. So I guess I'll take those as my answers, and of course you can prove this. But you know, this to me is better. Like exploring it by writing code and then playing around visually, I think is much better for the intuition than trying to work through the algebra and saying, yes, I can see the formula for the circle I get. All right. So moving back to here. And so now moving into how to use this to make interesting tilings, to make interesting patterns in the complex plane, observe that 2 points that are separated vertically by 2 pi will map to the same point under the exponential function. So like, in other words, the whole Euclidean plane here repeats vertically every 2 pi. And anything that's in any of those 2 pi slices, you can kind of mod out vertically into a canonical strip of width 2 pi and see that you get like, so if I draw something on the bottom there and I draw another copy here, you can see that they coincide. They're right on top of each other, right? Things that are separated vertically by 2 pi will land on the same spot under this projection. All right. So the upshot is like, let's bring in symmetry theory here. Any Euclidean design that happens to have a vertical vector of length 2 pi as a translational symmetry will project into a really nice seamless pattern under the complex exponential function. That's the one weird old trick. Take your favorite periodic pattern that repeats vertically with a period of 2 pi and just run it through this projection, and you can turn it into a spiral design. In fact, you can turn it into a whole infinite family of spiral designs, as I will show you. And in particular, take a periodic tiling, or even just any tiling that has at least translational symmetries in one direction. Take a periodic tiling that happens to have the vector 0, 2 pi as a translational symmetry, and put that in the plane and pass it through the exponential function. You will obtain I wrote a radial tiling here, but you'll obtain like some kind of tiling that grows outward from the origin of the complex plane with ever larger tiles arranged radially around the point, around the origin. And there are lots of ways to do this. So here I've got the tiling by squares, where I have exactly 6 squares lined up between z equals 0 and z equals 2 pi, or I guess y equals 0, y equals 2 pi. I take the exponential of that, and you'll see that I get circles containing 6 projected square tiles in each concentric annulus here. Of course, I don't have to just do that. I can tilt my square tiling 45 degrees, and now I have 5 squares diagonally filling up this stripe, and now I get, concentric rings of 5 projected squares that are oriented diagonally, which means that the corners of the squares point towards the center of the complex plane instead of the edges of the squares pointing towards the center of the complex plane. And in fact, you can generalize this completely, right? There's a generalization of this. So here's the technique basically in full. You start by just picking any periodic tiling you want that has these 2 primitive translational symmetry vectors, so V and W. And all I mean by primitive here is they are the 2 shortest non-parallel vectors that are translational symmetries of the tiling. We'll call them V and W. Next, take any 2 integers a and b that are not both 0. Doesn't matter what they are as long as they're not both 0. Here I have chosen a equals 2, b equals 5. No change to the drawing yet, but I've identified those vectors. Step 3, construct the vector AV plus BW. So it is an integer combination of the translational symmetries of the original tiling, and therefore, we all know from symmetry theory that as a result, that vector must also be a translational symmetry of the tiling, because it is a sum, or if you prefer, a composition of other translational symmetries. And that leads us directly into step 4, transform the tiling so that that vector is vertical with like 2 pi. So that's just a simple rigid motion plus a uniform scale. And, it's not so hard to do. It's just like, linear algebra. You can rotate and scale the tiling so that your chosen vector, AV plus BW, is vertical and has the right length. And then you're done. And then, anti-Mercator that sucker, and it turns into your favorite spiral tiling for today. And what happens here that's really nice, as you can see, when I started with either squares, aligned horizontally, vertically, or on the bias, I end up with concentric rings of tiles. But if I do something that's more tilted, then I get these, what were formerly the horizontal and vertical rows and columns of squares get transformed to diagonal lines in this stripe, and those diagonal lines become something like logarithmic spirals after you project them. So I get spirals of projected square tiles. You can see, hopefully you can see my mouse. There's one coming out of there, and there's another one coming out of there. And very famously, as we all know from phyllotaxis, there's a whole other set of spirals coming in another direction, which makes perfect sense because we have channels of squares both horizontally and vertically, and those channels should project to spirals in 2 different directions. Can I have anti-Mercator? I just noticed in the chat, you want the Samuel L. Jackson interpretation. Antimacator. Yeah, it's pretty good. If you haven't seen Samuel L. Jackson's recent commercial for wind energy, go look that up. He did a commercial for a Swedish wind farm company that is most excellent, but I will not repeat the tagline of the commercial. All right, so we exponentiate. And so I said, you get these spirals caused by horizontal and vertical channels of tiles. And in fact, the number of spirals in those two directions, at least when you start with square tiling, is precisely A and B, which is this really nice fact that allows me to dial up the numbers of families of spirals that I want. So I chose A equals 2, B equals 5 for this design, as you will recall. And sure enough, I have 2 spirals spiraling around clockwise, and I have 5 spirals counterclockwise. And you can sort of see that from the frequency with which these stripes have to repeat horizontally in, the horizontal stripes and the vertical stripes from the original squares repeat with that frequency and can be colored in, well, any which way. Now, when we, if you have done a lot of art math and you know the kind of the whole spiral phallalotaxis story, then you know that like plants, like sunflower seeds, like to arrange in 2 counter-rotating spirals that are consecutive Fibonacci numbers and stuff. And we always talk about the fact that there are these 2 spirals, 2 families of spirals in different directions. But the 2-ness of those 2 families of spirals is a little bit arbitrary. And I just wanted to point that out because I haven't really seen this anywhere, right? The fact that we see 2 families of spirals here kind of arises from the fact that we naturally follow these horizontal and vertical channels of squares in the square tiling. But if we switch to other tilings, like if I switch to a tiling by equilateral triangles, the triangles naturally form up into 3 directions of channels of adjacent triangles, which sure enough will give me like 3 distinct families of spirals in 3 directions instead of just 2. So here I have 2 families in one direction, 5 in another, and 7 in another for this particular anti-Mercator equilateral triangle tiling. And I was too lazy to work out, like based on A and B, you should be able to calculate the exact number of spirals you get in all 3 directions. But it just occurred to me the other day and I didn't work out how many exactly. Exercise for later. Okay, so I want to, this is the advertising component of the talk. I want to emphasize that like all of this is accessible to you in a piece of software that I wrote to go with the blog post that I wrote in 2019. I really wish there was a way to embed I want this to be a live web page running inside the slideshow, but as far as I know, there's no way to do that in Keynote. So I just switch over to this other view. Yeah, I'm going to give you all the links at the end here. So here is the software running live off of my web page. And basically what this is you take this whole anti-Mercator map stuff and you just crash it into Tactile, which is the library that I wrote to manipulate isohedral tilings of the plane. So this is an editor for isohedral tilings of the plane that then on the bottom left shows you the Euclidean tiling that you get with a particular choice of A and B. So kind of an oriented and scaled Euclidean tiling with, 0 and 2 pi implicitly as the top and bottom of this picture. And then the projected anti-Mercator tiling, the projected spiral tiling. And the nice thing about this is that the whole thing is live. So I can just go ahead and edit the tiling any way I want, and everything just updates in real time. It's a little bit clunky. I think it's designed for a touch interface. So to delete a point, I have to like long press on it, but that's okay. So this has all the features of like editing isohedral tilings. I can manipulate the tiling vertex parameters as they're called. This isn't a talk about isohedral tiling, but like to get a whole family of distinct tilings. And I can manipulate the shapes of the edges. And maybe most importantly of all, I can control A and B, right? So let's just start with this simple tiling by hexagons again. Here you can see I've chosen 1, 5, and sure enough, I have like one long spiral coming out this way, and presumably there's a direction in which I'll see 5 spirals going in another direction. And then there's going to be some third direction, I guess, depending on how I play with this. But yeah, I can easily just dial up different combinations of A and B in real time and see like different patterns that emerge. And I can do this for whatever my favorite isohedral tiling type today happens to be. So there's the Cairo tiling, same idea. The only thing you should never do with this program is set both A and B to 0. That is an unrecoverable error that I don't catch. I noticed that the other day. Just don't do it. And if I go to IH41, sure enough, here are my counter-rotating spirals by squares. So, you can, and like I said, you have this kind of 2-parameter discrete infinite family of patterns that you can get. You can also allow A and B to be negative, but I haven't done that here. Great. It's kind of nice. It's fun to play with. And it's all real time, which I think deserves at least, I should say, a little bit about how that is done. Because it's kind of, there are a couple of nice tricks in there. Oh, and I'll press the animate button later. The other thing I'll mention right here is it can apply colorings when you color the tiles. You can see like it's doubling up on the number of tiles visible on the bottom left there, and that's of course because when you color, you might need more copies of the uncolored fundamental region to make, or a translational unit to make a translational unit for the colored tiling, because the colors repeat at a kind of more sparsely than the tiles themselves. Okay, so, and you can't edit the colors. This is really just meant as kind of a visualization tool, I guess, but fun to play with. Okay, and yeah, and all real time. It doesn't really matter like how many tiles you're displaying, right? Still, ooh, there was a little bit of a bug there. Whoops, I went too far. So what's cool about this is it doesn't matter how many tiles are being displayed. The whole thing just runs at the same speed. And I want to say a little bit about how that happens. So just for the computer scientists or people who like generative art programming type stuff, the way this works is you've identified your tiling and it has 2 primitive translational symmetry vectors. Here, my primitive vectors are taking the coloring into account. So I have to skip 3 hexagons to get back to the corner of a hexagon that's the same color and same in this direction. And that implicitly defines a parallelogram that more or less contains 9 hexagons. And I want to draw a tiling with copies of that parallelogram. First thing you do, and this is an old trick, I wrote about it years ago. The first thing you do is you take that parallelogram and you render it as a square. So you render the geometry of the tiling under a transformation that skews and stretches and as necessary to fit that parallelogram to a square. So I get this skewed picture as an off-screen texture, but that's going to be fine. Because then I draw a single quad for which the texture coordinates at the 4 corners of the quad are carefully chosen to undo the skew transformation and give me as much of the tiling as I want to see. And it'll just sort of look like the original tiling when you render it on your computer's graphics card on the GPU. So the cool thing about this is every pixel is colored just using like a texture lookup, which means it basically doesn't matter how many tiles you show. This is the only thing you actually need to render that depends on the geometry of the tiling. Everything else is just texture mapping, which is essentially free on your computer's graphics card. So this can run like basically infinitely fast. It's not actually infinitely fast. It's just really, really fast. And in fact, the anti-Mercator part, the spiral part, is basically just as fast, which is incredibly cool. The spiral tiling part is rendered using a custom fragment shader that basically remaps through the anti-Mercator map and then does the texture lookup as before. In fact, it's slightly more complicated than that in a way that's slightly interesting. What you do is, given a point in the complex plane, you don't apply the complex exponential function, you apply its inverse, right? This is a pretty standard thing you do in computer graphics. We start from the kind of the range in which we're operating, the complex plane, and we undo all the transformations that got us there to decide where in the original Euclidean tiling we want to look up for that pixel in the final drawing. So I apply the complex logarithm to get from the final spiral tiling to a point in the infinite stripe between 0 and 2 pi. And then I take that point and pass it through a change of basis into the basis given by the translation vectors of the original tiling, which essentially gives me a point in this texture, well, in an infinite plane covered with square copies of this texture. And then I use the texture hardware to read this texture modded out by 1, which is built into your graphics card because it says, sample this texture with periodic boundary conditions. And so it sort of goes from here to here, back to here, and then picks the right point in here to draw to use for this point in the final picture. And again, you can draw as much of this anti-Mercator spiral tiling, doesn't matter. Like the constraint is the number of pixels, but pixels are basically free. So which is very cool because if you try to draw the individual tiles, spoiler, there are infinitely many of them. So you could decide to stop when the tiles are 1 pixel large, so you know they're too small to actually see. But this way, you just go pixel by pixel. It's a little bit, I think Vladimir talked about something like this last month. Similar idea here. Okay, I better get through. I'm making okay time here. I see, yeah, I see. So pixels are easier. I see in the chat. Yeah, it's easier than the geometry. So it's easier to sample backwards from pixels to the original geometry than to push the geometry through into the projected tiling. The one thing that's hard to do in this world is to get constant width edges because the edges scale in width along with everything else as it's scaling. So if you want constant width edges, you have to do something much more clever at that I have not tried to do, but you'd have to like measure the derivative and like programmatically vary how much edge you draw depending on the local scaling factor. And Charlie asks, like, have I tried texture filtering? I have not added texture filtering to this. You could. I just like, yeah, it's a little bit too complicated for me to bother in the context of this demo. But you could do some texture filtering here. I mean, at the very least, you do some mip mapping. Yeah, and Vladimir points out the derivatives are free in the fragment shader as well. So you can probably get away with constant thickness, although I do sort of like the variable thickness here. All right, let me move on from there. So the cool part about this is both the Euclidean and the spiral views in this app are like as fast as they could ever possibly be, which allows you to do all this editing in real time. It's kind of nice. Of course, there's nothing special about manually constructing a periodic tiling using something like Tactile. That just happens to be the tool that I have around, and that, you know, I wrote that blog post in 2019. I made the new JavaScript version of the Tactile library in 2018. So if anything, I was looking for an excuse to put it in things. And this just seemed like a really good opportunity. And I should say, like, you know, one of the reasons I made this blog post and this app is because of what I said earlier about, like, this is a thing that maybe looks complicated when you first see it, but turns out to be quite elegant using this one weird old trick. Well, the problem is I was reviewing a lot of papers that were like taking the path of greatest resistance. They were trying to derive the shapes of these tiles like directly in their spiral formation. And that takes a huge amount of work. And so I want to say, like, just do this, right? This is the simple, elegant way to solve this problem that 99 times out of 100 will give you all the information you need about the spiral tiling without having to think directly in spirals. Okay, so there you go. But there's nothing about Tactile that, you know, that is essential to this process. As I said, you can really start with any periodic pattern. So I have to demonstrate that. Oh, I quit my talk for no good reason. Let me just start that up again. Sorry. Get that out of there. What I wanted to do was go to here. Here is a quick second demo I wrote. This is a quick hack based on the first demo that I threw together late last night. But you can see, I mean, this demo takes, like, as input an image instead of constructing the tiling, and that image takes the place of that skewed picture that I used to drive the process when I was using Tactile. So I just cut out one translational unit from this Escher tiling, and it's sort of approximate, but it's a nice old trick that gets you like sort of allows you to apply the apply this process to any Escher tiling that you want, as long as his drawing has at least one complete translational unit. And this is a bit of a hack. Other people have done this much better. If you look at like the work that Jürgen Richter-Gebert has done with like eye ornament and hyperbolization of Euclidean ornaments, he like will process the input image and kind of average it out to get sort of the best possible repeat unit that actually repeats seamlessly. If you look closely, you'll see seams here, but that's okay. So I have that, and I guess I should do the birds as well. Same idea. A little bit rougher, the seams are more visible. But yeah, it works fine. You can spiralize any Escher tiling you want. That's kind of neat. Let me go back to here now. Okay. So just a couple more tricks to mention. Of course, why settle for one infinity when you can have two? This is another old trick, and I think Vladimir showed this as well. You can take the entire spiral tiling and apply a Mobius transformation to it that basically drags the point at infinity over next to the limit point that you already have in the spiral tiling and creates a second limit point next to it. And by doing that, you can get these beautiful like S-shaped spirals that with these designs that have two limit points. Again, not really a new trick, a very old trick, but a convenient way to get pretty patterns using this tool. So in fact, well, let's make that less crazy. I do that, and this will be clear if you play with this tool for more than a couple of minutes. All you have to do is click on the spiral drawing, and you get the double spiral version with a Mobius transformation. So there you go. That's fun to play with as well. The spiral, the two limit points are chosen to be in the upper left and bottom right. Sorry, you can't change that. But it's just a demonstration. Okay. So you can't have three infinities. You have to, like with this technique working by itself, two is the most you can get. Sorry. This does relate to some of the other stuff that Escher did. So he did experiment with two infinities in the print whirlpools. I'm not 100%. In fact, I'm doubtful that this whirlpools design is actually like makes sense using the construction I just showed you. It might just be sort of draw an S-shaped double spiral and then fit fish to it. So it's not truly an example of what I just showed, but you could come close, I imagine. And then sphere surface with fish. Well, this is a 2D print of what looks like a 3D sphere, and that this actual design on the 3D sphere that would have a limit point on at the north and south poles would, of course, be drawable by taking one of these spiral tilings, putting a sphere on top of whose south pole is sitting on the limit point of the spiral tiling, and performing a stereographic projection from the spiral tiling up onto the sphere. So the limit point at the south pole would be a copy of the limit point that it's sitting on top of on the spiral design in the plane. And then the limit point at the north pole would be gathering up everything at infinity in every direction and bringing it up to the north pole here. And then you project that down to 2D, I guess, and you have a 2D design. Okay, wrapping up, one more connection I definitely want to make is that Escher implicitly explored the connection to the complex exponential function in other places, most notably in his mind-blowing print gallery. And if you haven't seen, there's documentaries and magazine articles about this, about the work of De Smet and Lenstra, talking about the connection of this to the Drost effect of having nested infinite pictures in picture. And the complex exponential function plays a role in here as well. And you can see in the work that De Smet and Lenstra did to take apart this drawing, the core design that they use is this periodic Euclidean texture and I've highlighted one translational unit here that captures all the information in the print in such a way that like successive vertical stripes of this pattern represent successively nested copies of the scene, nested one within the other. And if you kind of tilt the whole thing using a particular choice of A and B and take the complex exponential function, you get back the original print gallery minus, right, including, I guess, the extra stuff that ought to go in here, where Escher very cleverly left out and just signed his name. So that's a connection too. I should say just a little bit about animation. Obviously, if I have a pattern in the Euclidean plane that repeats vertically with period 2 pi, any translation of that repeats vertically with 2 pi as well. So you can translate at will, however you want, and get an animation. So if I press the animate button here, all this does is it slides the tiling along its direction of translational symmetry, and that will cause, because that direction happens to be diagonal, that will cause this like spiral, scaling, twisting motion, which is really nice to look at. If you do that, this is much more trippy to look at. Sorry for the low frame rate, but if you do this in the to infinities view, it looks really cool. I'm going to stop that. And just as a demonstration of this, I'll show two examples that came from Adam P. on Mastodon. And I know this because he added me and said I use techniques similar to this blog post by CSK. What's cool about this, of course, is now that you know the trick, that this is all complex exponential function, it's much easier to imagine how you might draw this, right? This is clearly like just a pattern in the Euclidean plane that is sliding horizontally and with stuff changing inside the pattern depending on its horizontal position and doing so periodically. And here's one more. This one's just a little bit more complicated. This is clearly using the double infinity extra Mobius transformation, and it's using a square tiling, but adjacent rows or columns of squares are moving in opposite directions from each other. And the rest is all beautiful, dazzling special effects. Really pretty, actually. I was going to make a couple of these by way of demonstration, and I realized, why am I doing that? These are already beautiful, and I'm happy to show them. So go look at those online as well. All right. So just going back to here, I haven't heard any bells, which is a very good sign. So let me wrap up. I'm going to grab all the URLs you see there for reference, and there they are. So that's that. So just to wrap up quickly, I want to promote this because this is a nice combination of, if you take a complex exponential function, you sprinkle on some basic ideas from symmetry theory and periodicity, not aperiodicity, periodicity, you get this kind of nice space in which to play. It's great for illustration. It's great for mathematical art. It's great for looping mathematical animations. It has this rich connection to MC Escher and the quest to represent infinity. So it's been something I've liked to play. I've enjoyed playing around with for, well, more than 20 years now. Some links. There's a blog post that I wrote about this in 2019. You can go find that. There's more or less what I just said, maybe a little bit different. There's the tool that I showed at the beginning of the talk that lets you just doodle in the complex exponential function. And there's the full Let's Draw Spiral Tilings tool. And if you want the links for the Dixon paper I mentioned, or for that matter, Print Gallery, there they are. Okay, that is it. So thanks for coming and watching. Have a great holiday. And I'm happy to chat some more, take questions.
Thanks, Craig. That was gorgeous. There was a lot of activity going on in the chat. I didn't catch it all, yeah. Oh yeah, no. I want to give folks a chance to hop in and ask some questions. I can also mirror some from the chat, but first let's open it up. See if you can unmute yourself and just holler if you'd like.
Oh, thanks everybody. Everybody got there.
So one question that I would reflect was from Uttam Grandi, who asked if there was a way to export the outputs of these as SVGs.
Yeah, so The online, the tool that is installed on my web page, can I go back to that? Yeah, you will notice there is a save button that saves this, but saves it as a PNG file, which is okay. But yeah, people want, I mean, of course, you want geometry. Let me see if I go to, so if you go to localhost :8000, it won't work for you. This is my computer, not your computer. There is a prototype version of this tool where the save button outputs an SVG file, not colored in, and in this case, constant width edges. And what's cool about this is if you import that SVG file into Adobe Illustrator, you will discover the really neat fact that like it doesn't work at all, because like we're using as SVG inside baseball, we're using X-links, whatever, we're using instancing in the SVG, which Illustrator just like loses its mind over, which is kind of unfortunate. But it is possible. So in fact, what I did to make some of the diagrams in the talk, take this SVG file, save it as a PDF, like print it to a PDF from the browser, and Illustrator was happy with that PDF. Now, how is that helpful to you since you do not have access to my localhost? If memory serves, the version in the Tactile JS repository on GitHub, I think might have the SVG stuff in it. So if you run this yourself, yeah, so it does, it saves to SVG, not PNG. So that's kind of cool. It really should be able to do both, but yeah, this was the work of an undergrad. I hope I don't get this wrong. I think it was Nikki Hazrati who added this to the code around like 2019. So yay, Nikki. Yeah. So yeah, a little bit more work involved to run this yourself, but it's there.
Cool. I saw Matt, you raised your hand.
Yeah. So right as I raised my hand, my 3-year-old started coming in and making noise, so I had to close the door.
Cool.
Yeah, great talk. I really enjoyed it. I have a question, maybe not that well thought out. But no, gosh, he's out for an hour now. Could you go back to that slide in the very beginning where you first say one weird old trick?
Sure. Where's that?
Yeah, hold on a second.
It's cool.
Yeah, just something. Okay, so when I first saw this, my initial thought was like, oh, can you do this with an aperiodic title? Didn't know what the weird old trick was. Once I saw that, I was like, okay, obviously that's not going to work. But now I'm looking at that thing in the bottom right, and I'm thinking, could there be an aperiodic version of that? And if so, is there some pre-image of that, not maybe under that map, but under some other map? Is there a way to associate that with a standard aperiodic tiling? I don't want to make you break your promise about not talking about these things, but that's something I was wondering about. Is like, could you have this spirally hyperbolic aperiodic tile, and what would that pull back to?
So there is a connection that you can make here. 2024. Yes. So in fact, in Bridges 2024, there's a paper called Periodic Strips from Aperiodic Tiles that says, even if a tiling is aperiodic, you could still like make a strip that repeats in one direction, like as thick as you want. So, so I could, in principle, like this strip here that repeats periodically horizontally, I could turn that 90 degrees and line that up with my 0 to 2 pi strip in the complex plane and take the anti-Mercator of that. And effectively, so this isn't quite what you were asking, but it does at least allow me to get annuli of aperiodic tilings within some constraints. Like I can't necessarily choose the sort of, if you tell me like how thick you want this to be, I don't necessarily get to control how wide it is. So I can't make it an annulus that's arbitrarily thick, but you could play some nice tricks with aperiodic tilings in this way. As for like another transformation that like does something cool, that's Yeah, that's much less clear. Beyond tricks, I'm not sure. Yeah.
It doesn't seem like there'd be one, but like there are special cases, and the one you just showed is one of those.
Yeah, but like to do something to the entirety of an aperiodic tiling, that I'm not sure I can see how to do. Like, there's probably some very cool, complicated cohomology tiling space thing that comes into play here that I don't know about.
Yeah, there's a response in the comments. I was just thinking,
Yeah,
like, if you had one of these hyperbolic aperiodic tilings, like, how would you map? Is there something that does map back to that's Euclideanish? But
yeah, it's that. Yeah, I don't. It's not clear to me. I'm not quite sure what Royce is getting at, but it'd be
Very good
interesting to.
question. I mean, for aperiodic tilings made by the cut and project method, basically you might be able to embed. So you start with like a periodic structure, then you embed a projection cut, a sliced plane essentially. As long as uh, the angle that the plane makes with the root vectors of the embedding lattice,
Right.
as long as it's incommensurate at irrational angles, then you'll get something that's aperiodic. What you could do possibly is align one of the vectors of
Yeah.
that embedding plane to be periodic with one of the vectors, and then the other one to be incommensurate. You might get something which is periodic in one direction and aperiodic in the other, and then you can get a strip that way. I'll look
Yeah,
into that.
you could get. I mean, doing that, you don't even necessarily get a strip. You would get an infinite tiling that has one direction of translational symmetry potentially. I think.
Right.
Um,
I think
yeah,
too.
I've thought about that. I haven't ever tried to do it. Like with Penrose tiles, what would happen necessarily if you twiddle one of the vectors to be just sort of a rational number close to the golden ratio or something like that?
Uh-huh.
I think what happens is the tiles are very slightly deviated from rhombuses, right? They're sort of a little bit parallelogram shaped. Um,
Mhm.
but you get a kind of periodic tiling that is similar looking to a Penrose tiling. And I've always wanted to try that, but I haven't figured out the easiest way to do it.
I mean, another option I can think of if I can jump in is so uh, Olga Pyrus-Muskovich talked a lot about these sort of like what is it like Novikov patterns or something or Novikov something where you take a plane through like a gyroid in 3 dimensions or something like that, and if the plane is irrational, you get a periodic pattern because like the gyroid splits space into 2 parts, and then you can color one part of space black and the other part white, and then
I haven't seen that.
so you get a triply periodic thing in space, and then cut it along an irrational plane. And if you instead cut it along an irrational cylinder, then you now have a cylinder that you can conformally project to that punctured plane and get a one of
Right.
these exponential patterns.
Yeah, that would
Which
be
should
an
be
interesting way to get kind of more kind of wild patterns via projection. That's cool.
yeah.
Yeah, it would work, I think.
I have code like shader code that for rendering the pattern just on a planar slice. And so maybe if I have time at some point, or I can just sort of
Is that
the
on
code
Shader
is
Toy?
the code is open. No, I don't have it on Shader Toy right now. I think it's only on like my a presentation on my website, so you have to dig into the
Okay.
JavaScript. But I can try to put it on Shader Toy so that somebody could
Well,
modify it to do the cylinder thing.
give us the link. We demand the link.
Yeah. Okay. I'll try to put that in the Discord
Yeah.
chat.
Cool.
Hey, Craig, do you mind if I take a sec to explain what I meant to clarify?
Is that Royce?
Yeah.
Oh yeah. Yeah, please.
So if you imagine the entire aperiodic tiling in the plane and unstereographic projecting that onto the sphere, it kind of feels like it's converging, even though it's not converging to something at the
Right.
North Pole. And then you rotate the sphere around to put that at the South Pole is what I was trying to describe there.
And then yeah. Yeah. So you basically like the whole thing kind of falls apart, but it falls apart at infinity where you can't see the error.
Yeah.
Like that. Yeah, that's totally worth trying. It's like a Penrose tiling everywhere and with like a breakdown. Yeah, should totally do that. That's good. Come on, somebody post that. What does that look like? Somebody's got to throw that into the chat like on the fly. Can't be that. How hard can it be?
All right, we've got homework.
That's a great idea.
Yeah, this is awesome. And I love the conversation that it started. I would say that it is maybe 1:12 my time, and I have to run off by 1:15. I don't know, Aaron, if you want to keep it open, but the Discord continues to exist, and I encourage folks to continue to chat over in Discord. There's also voice chat there if you wanted to hop into one. But yeah, thank you so much for such a wonderful talk. Thanks to all three of our speakers. Today was just an incredible way to end the I'm So year. Aaron, do you have anything else to say before?
No, just to echo the thanks. Appreciate the lovely presentations, and thank you all for showing up and making this all happen. And once again, we will not meet in January, but we'll see you all in February, one way or another. So I will stop the recording and take care, everybody. Have a good holiday, and see you next time.